Back in database mode. Deadlocks are like deadlocks are that blocking traffic jam in a circle. If there's ever a circle in that traffic jam, then no amount of patience is going to solve that problem. It's like a traffic jam forever. So, but it hurts because SQL Server will actually detect these things and pick one and fail. And so they don't, deadlocks as a problem don't look like the server has gone away. They look more like the error that pops up now and then. When is it a problem? Well, when you can't tolerate the number of error messages coming back from your application. In some applications, you may have a tolerance of 0 error messages. All right? So let's look at these deadlocks and what they kind of look like. We have 2 processes that want to do something to 2 different resources. It's pretty common. When I draw an arrow like that, it takes a lock on that resource. It's reading a row or it's writing something. And the other process does the same thing to someone else. So the first one has to wait for that second process. But at the same time, see where this is going? The other guy has to wait on this. I've shown 2 processes and 2 resources. It could be 3, it could be 4, it could be many. SQL Server will wake up periodically and look for blocking chains that result in a circuit. It will, if it finds a circuit, it has to do something about it, right? It will kill one of the processes. It won't do anything to the other one. Like 1 out of 2, like 1 out of 2 error messages isn't bad. Well, at least it's better than 2 out of 2. When that guy gets killed, all the locks that it had are released, and the other one is allowed to continue. All is right, well, at least for that second guy. Now that first guy got an error, and if you had good eyes, you could have seen the error said transaction process ID 83 was deadlocked on lock resources with another process and has been chosen as the victim. Rerun the transaction. Now SQL Server, Microsoft's already giving you a hint of one of the strategies you could use to tackle this problem. Rerun the transaction. So to tackle deadlocks is very, very tricky because you need to, it's not something that you can debug slowly because deadlock stuff involves a race condition. Right? It's very, very hard to deterministically create a deadlock that happens. So what I find works well is 1, collect the deadlock graph. The graph is another way of saying let's go back. Deadlock graph is, I'm calling this a graph because it has nodes and edges, the mathematical graph. But if I just have this information, this is all the information that I want. I want to know who both actors are. What resources were they fighting over, right? If I just look at the one process that got killed, I don't have all the information. So collect the deadlock graph is imperative. That means that we'll show you how to collect the deadlock graph, and if you haven't got this set up ahead of time, then you're going to have to set up configure deadlock graph collection, and then wait for the error to happen again. After you collect it and you understand what's going on, reproduce it reliably. Being able to reproduce it reliably involves, the best technique that I've found is to write a program, and it has to be multi-threaded. You can't write a single-threaded program that accomplishes this deadlock. Reproduce the deadlock reliably by writing a program that just hammers a test system using the actors and resources that were involved in the deadlock graph that you saw. After you reproduce it reliably, now you can begin to do experiments, and you have to tackle each deadlock on a case-by-case basis. And this every database is so different that you have to tackle them individually. It's like every happy process is, all the happy processes are all alike, all the unhappy processes are different in their own way, kind of thing. Another way of saying that is, I can't, by inspection, tell you, looking at a deadlock graph, what technique will work in tackling them. Aside from the retry. The retry mechanism that you have to write. SQL Server won't handle retries for you. But if you write a program to capture errors and retry a transaction, that technique will work. But I use it kind of as a last resort. All right. So rather than further explain what deadlocks are, I'm going to show you what it looks like to tackle some of them. All right. We've already seen some when I ran my program. Transaction such and such was deadlocked on lock resources. Try it again. All right. So we see deadlocks. So we're going to configure SQL Server to collect the deadlocks. And we're going to use extended events. There are different methods, but we're going to use extended events for this. Just like the block process report extended events session, I'm going to use new session wizard. I'm going to call this Deadlocks. I'm going to start it immediately. I'm going to search for deadlock events. Now there's a bunch. You want to use the XML deadlock report because it has all the information. It's the deadlock graph that we were talking about. We're going to store this stuff in a file and start it. All right, we're collecting deadlocks. Let's reproduce. Clear the screen. Let's reproduce it. We have to wait a while. SQL Server has to wake up. Oh, found some. Let's wait a little bit more. Found some more. Okay. I'd say we've reproduced this enough. Now let's look at our deadlock extended events. Sorry, yeah. Here they are. Let's see. Now this is the XML report, but there's something special about this particular event. It's this tab here, right? When you click that tab, you get the graph. Now I use ovals and rectangles to try and make this graph seem a bit familiar. You're not expected to read this part. Luckily, this had two processes and two resources involved. Let's look a bit closer. I've got an example that I created earlier. You can zoom in. The resources involved were lessons progress and the table lessons. Okay. The rest of the stuff here, it's kind of hard to drill into this. What we want to know is what queries were involved. In order to look at that, we have to crack open this thing and look at the raw XML. The XML has all the data. It's going to look daunting, but don't be afraid because we ignore most of the data. If I zoom out, so you definitely can't read it, you'll notice that there's two parts. This is the process list. It lists the two queries that are going on, and the part down here is what they're locked on, what they're waiting for. The only piece that I'm curious about here is this query, the update lessons, which is being executed in update lessons progress. We've seen that one before. And this one, which is a select statement, and that's from get lesson progress. Okay? This is where we have to dig into what SQL Server is doing. We're going to use that. We're going to do that using execution plans, or other people know it as query plans. In Oracle, it's called explain plan. Other people have other ways of showing the guts of how a query gets executed. But we're going to use query plans to dig in further to what these two queries are doing. All right? Right. So I use Control-N to collect the query plan from Management Studio, or I could just use this button here. When I do that and execute one of the queries, I get this new tab which shows me the execution plan. What do we see about it? Well, it's reading from lessons progress. It's writing to lessons progress. It's reading from lessons. You don't have to remember this stuff. And then it's reading from enrollments. And down here, it's reading from a TVP, it's reading from lessons, and then it's writing to lessons. All right, that was the one side. The other side is a little bit more simpler, a little bit more simple. We execute it, look at the query plan, and we see that it's reading from lessons and then reading from lessons progress. All right. So if I wrote that down, it looks like this. And I also noticed, based on the queries that we're executing at the time, that the deadlock and the resources that were under contention, with a lot of thinking, I can identify those two activities as the activities that are waiting. And they're waiting on locks that were acquired during these activities. No amount of waiting is going to free the other guy. So here's one technique which is going to work in this situation. I recognize that logically I can adjust the query to swap those two activities around. There are two queries which logically it doesn't matter how I execute them. One's a merge, one's an update. This follows the rule of thumb: do as many reads as you can before you do your writes, and read your resources in the same order. That's easier said than done, but we're going to try it in this case. If we swap those two activities, all of a sudden we get waits that look like this. One can't wait on the other indefinitely. This stuff does have a blocking chain, right? But it's a blocking chain that doesn't last very long. The locking is important to coordinate access to resources, but it doesn't last very long. All right, so we're going to see that in action. Here's the text of, there we go. There's the existing text. We're going to alter this procedure. And we're going to swap the merge with the update statement, because we recognize that we're lucky that we're free to do that. It's in a particular transaction, it's actually not, it's atypical that the order doesn't matter. In this case, we see that it does. All right. We've adjusted our procedure. clear screen. We're going to run our workload. No primary key violations, and no deadlocks. We're in a good spot. This is good news. No errors coming back. All right, cancel. There we go. So, I mentioned a couple strategies. Be careful about the way you access resources. That's carefully order your modifications. Tuning your queries is my favorite way of avoiding deadlocks. For two reasons. When you tune your queries, typically the database, say you apply an index, which means your query is processing less data. It's looking at your index and only looking at a small set of rows, and your query returns faster. When you do that, it means you're locking less things, less chance for conflicts. Also, it means that the duration that you're holding these locks is much shorter. Now, even though when you reduce the duration of a query from, say, a few seconds to milliseconds, the chance of two concurrent queries actually overlapping becomes far, far less. And although it's not reduced to zero, I've had it close enough to zero that it might as well be. It doesn't feel right, but this is my favorite way of avoiding deadlocks, tuning your queries. Read committed snapshot isolation. Read committed snapshot isolation is what I think of as Oracle mode. It means readers don't block writers, and writers don't block readers. I encourage it for any brand new development. I wouldn't turn it on immediately for existing databases because the behavior is a little bit different. It's a little bit different in this way. If someone is writing a row and has a transaction open, and I want to read that row, SQL Server makes me wait until that transaction is either committed or rolled back. With read committed snapshot isolation, it changes the default behavior of read committed so that it no longer waits. It receives, I get to read the value, but not the one in flight. I get to read the last committed value of that row. Okay. It's as if the old behavior is as I decide to edit a Wikipedia article, and while I'm editing it, no one can see it until I save my changes. That's old behavior. The new behavior is I decide to edit a Wikipedia article, and everyone gets to see the old version until I save. Then people immediately see the new version. That's the way Oracle works by default, and it's the way that Microsoft wants SQL Server to work by default, but because they value backwards compatibility so much more, they have to leave this as a config. And this kind of this feature helps avoid reader-writer deadlocks. And like I said, look for X and S in the deadlock graph. X is an exclusive lock, which represents the writer. S is a shared lock, which represents the reader. Use covering indexes. If you ever have a key lookup and you see that in your explain plan, it means that you're using an index, and then SQL Server is looking up the rest of the data in the table. So imagine I have a users table with an index on last name, and I want to know if there exists a user in that user table named Michael Swart. It'll take Swart, it'll look up the index, and it'll look up the rows with the name Swart in the table. If it sees any Michaels, it returns yes, otherwise no. Now what if I had an index based on last name and first name? Then it looks at the index and it sees Swart Michael. It already knows enough information to give me the yes or no without having to look at the table. This falls under the category of reading less rows, because reading in an index and reading a row in a table, or the clustered index, you reading less rows, it also counts as tuning. Falls under that tuning your queries there. We call it covering because an index satisfies the query that you need without having to use the table data. Last resort, implement retry logic, and I talked about that. All right, before I move on, let's talk about deadlocks. Any questions about that? Yeah.
Have you ever seen the SQL engine not detect deadlock when you have a deadlock in a complicated deadlock scenario?
Never ever. I have seen super complicated, thousands of queries participating in a deadlock circuit, and it's always found it. And it might have to kill more than one process, but it is, that part is solid.
Yeah. I'm just asking because I ran into it. I would have loved this information before because everything you went through helped us solve the problem. We actually had a deadlock that would not be resolved by SQL Server, so we changed the whole database over to use snapshot isolation in conjunction with a bunch of things like covering indexes and whatnot.
Interesting.
But yeah, the whole thing's down completely. The whole application goes down in a lock state with zero CPU usage and SQL Server is sitting.
I'm
So
very surprised at that.
SQL 2008 R2.
If that's the case, I expect that to be a bug, and if the product team knew about it, they would have jumped on that immediately, run around and get a cumulative update or a bug fix out very quick. Personally, I've never seen that.
Yeah, it was painful.
The pain you're talking about is the pain I felt too. Most of these lessons come from my pain, so I'm sharing those lessons.
Yeah, like I said, it's very, very valuable. All these strategies were helped solve the problem.
Yeah, I empathize. All right. Tempdb Contention. This is specific to SQL Server. If you choose another database platform, you may have other kind of problems, but Tempdb is specific to the Microsoft world. I blame Microsoft for this whole category.
Not Sybase?
What's that?
Not Sybase? Sybase around?
Yeah.
Because it's Sybase's design.
I blame all of them. Okay, Tempdb is often used for, surprise, surprise, temp tables and table variables. That's not surprising. They do land in Tempdb, both of them, always. But Tempdb is used for everything else that gets persisted. Everything else that doesn't belong in your user databases goes to Tempdb. Includes stuff like when executing a query and it needs to sort, it's too much to sort properly in memory, it uses Tempdb to spill some of that. Same with hash joins, that's where the hash goes. Large object data, spooling, static cursors, lots of this stuff. All these features use Tempdb. It's like the public, it's not a good place, but all the data gets dumped there. At my work, we typically find Tempdb contention based on our usage of table value parameters. This may not be applicable, but it's fun to talk about, or rant about, I guess. So let's get into it. That's what Tempdb is used for, and contention comes. Oh, the other thing is that while you can isolate databases by application, you can't do that for Tempdb because there is one Tempdb per server. So if every app needs Tempdb, every app will create its temporary objects in that single database. It means that while we kind of scale out to the size of the server by using separate databases, Doesn't work for Tempdb. All right. Here's how the contention works. Tempdb is a regular database. Databases have two kinds of files, data files and log files. The diagram I have up here is a data file. Right? Our data files in this database and every other database is split into 8 kilobyte sections. Every 8 kilobytes section is called a page. 8 pages make up an extent. And when you create an object or anything else in Tempdb or in any database, SQL Server will allocate a whole extent for you. And so it needs to keep track of what's allocated and what's not allocated. And so it does that in something called the allocation map, the global allocation map, which is on every database file, that second page. That second page keeps track of the allocation status 1 bit per extent. And if your data file happens to be larger than 1 page's bits of extents, then it'll create a new global allocation map. When you create an object, it has to update that page. When you drop an object, it has to update that page. So deallocate stuff. If you're creating objects often and dropping them often, you have to update that page and often. And so there's another kind of allocation map, and it's that first one. It's called the page free space. It's 1 byte per page. It kind of keeps track of allocation status, roughly how full the page is, and same deal. Now it's interesting that this is not an I/O problem. Every page can be changed in memory and has its own copy on disk, or vice versa. Every page on disk has its copy in memory, when it is in memory. When it's in memory, a page is called a buffer. I don't know. That buffer doesn't always match the page on disk, as long as the changes are written to the transaction log. A checkpoint will consolidate everything and dump all these dirty pages to disk. But it turns out Tempdb doesn't really need to use checkpoints unless there's a memory pressure problem. And so Tempdb actually doesn't use a lot of I/O, like actual physical I/O. So the contention still exists. It exists by processes trying to take a lock on those allocation pages in memory. And when the lock is on these pages, it's called a latch. So these buffer latches, it's kind of like page locks. But it's not an I/O problem. So whenever I complain about Tempdb, even the Microsoft people says, "How are you using your SSDs for your temp?" It doesn't matter. It's a memory thing. It's about a frequency thing. It's actually not about how large the objects are that you're creating. It's about the frequency. And again, we're talking about thousands a second. Again, 1 Tempdb per server, not per database. Unlike other databases, Tempdb objects are created and destroyed often. Every time I use a temporary table, create and destroy. You typically don't create and destroy objects in user databases that often. Personally, we deploy new software roughly monthly. And so our changes to our user databases are typically once a month, unless we have a hotfix or something like that. You guys may have more frequent deployments or less frequent deployments, but user databases are typically not a problem for this kind of allocation contention. Tempdb is another story. Read-only queries in your user database can sometimes turn into read-write queries in Tempdb, especially if you use table value parameters. some of you may use table value parameters, some of you may not. Table value parameter uses a table type. So just like int, just like string, you can create your own types. You can create a type which is a table, an int set, which is a table which takes a single value of int. We use this often in order to pass sets of data to our procedures. So for example, give me the number of attendance data for users in this class list, and I'll give 10 user IDs to get back the data I want. That's the typical way we use table value parameters. Our procedures will have a signature that looks something like this. A number of parameters plus a table value parameter as the second one. Any questions about TVPs? Yeah? But you can get into trouble, like I've described. Microsoft has this advice. Enable trace flag 1118. It's a magic trace flag. I'm not going to get into why that helps. It's on by default in SQL Server 2016. It has no downside. So just turn it on. Increase the number of equally spaced Tempdb data files. I'll tell you why this works. If I have 8 data files, all of a sudden all my Tempdb activity is distributed to those 8 data files equally. It means that the activity on the allocation page is reduced to 1/8 of what it used to be. That actually works. We create the physical data files so that we get that buffer in memory. So we have 8 buffers in memory. We have to create physical files in order to achieve that. That's annoying. Like I said, this is Microsoft's fault. And the third thing they say is make changes to the workload or code. In other words, doctor, it hurts when I do this. And the doctor says, well, don't do this. Easier said than done, and it gives you no way to process. Yeah.
Well, I had a similar circumstance where I needed to send sets of data to my stored procedures.
Yeah.
But basically just because I was lazy
Yeah.
and hadn't used table value parameters, I chose not to. I just send this XML, and I parse the XML. Then I'm loading that in a temporary table.
Yeah.
Now, is the temporary table would, unless it gets very big, would always be in memory, right? Is it the size of the table value parameters
Right.
that's putting them on
So-
TVP?
So the problem I'm describing here is all about frequency. If I'm doing something, say 5,000 times a second, then I have no capacity to use any table value parameter that is going to have a number of rows more than like a dozen. Right? These have to be short and sweet. The example that you're thinking of, how many times a second are you calling this?
In the particular application that I used, it was,
Once a minute.
yeah,
Not
maybe,
even.
maybe. Yeah.
You don't have to worry about
No, I
this kind
understand,
of
but
problem.
conceptually, I'm just wondering, is that actually a solution
Yeah.
to the problem because it now takes it out of TempDB?
No.
I'm unclear on all of the
The processing of anything that doesn't go into your user database typically goes into Tempdb. That includes the data used for processing that XML parameter. It also includes that temporary table that you created to store that.
Oh, so those are
All
in
of that
there. Okay, that
goes
was my
into
question.
TempDB.
Okay, yeah. So they don't just sit in memory.
That's right.
Because they're internal to a stored
They,
procedure.
they are in memory because they're going to be anyway,
Right.
but they do get written to Tempdb. Now, the data pages don't get flushed to disk, but the log file does. The log file tracks any kind of changes, and that gets written to disk as well.
There's no required persistence for this, though. But it's
Exactly.
being persistent
But there-
anyways.
but
Oh, okay,
there
okay,
is
no,
anyway.
okay, that's my question. Okay.
It's like,
So I didn't stumble on a solution.
No.
Okay.
there is an opportunity to not write to Tempdb, and for the longest time, Microsoft did not take that opportunity. But stay tuned. All right. let's look at what that looks like. How does it hurt? Tempdb contention is worse than performance degradation because we can go from, as you increase the load, you get sort of this capacity of the amount of activity you can support. And when Tempdb contention hits, all of a sudden the capacity drops. So it's not a cap on your activity. When Tempdb contention hits, it's throttled further than what it was just moments ago. So it can look very, very painful. It can almost look like your whole database has gone away. So let's look at what this looks like in real life. So we run the workload, and when we look at performance, we're getting about 4,000 queries a second. Let's say we're not very happy with that. All right. The first thing we do is use SP who is active. All right. There are no rows here. Let's try it again. That took 4 seconds, and there's only 8 rows. That's your first clue. SP who is active lags a bit, and the data is incomplete, but you might not have any indication that the data is complete. I expected 500 queries or so, and I only got 8. Here's what's going on. SP who is active itself uses Tempdb. SP who is active waits until it can get the resources it needs to run. And when there's a lull in the activity by accident or who knows why, it's finally allowed to run, but at that time, we're not getting a clear picture of what's going on. When SP who is active itself is slow, that's my first clue that Tempdb is involved. So what I'm going to look at is the wait statistics. SQL Server itself tracks when it waits and in which categories. Right now I'm going to clear the waits. I'm going to reset all the categories to 0. Now let's wait a little bit. It's been about 10 seconds. So here are the categories sorted by wait time. The top category is page latch. It wants to update a page. It wants to get a latch on it. And by far, by at least 2 orders of magnitude, it's waiting in this category. We can actually ask, when you're waiting, what are you waiting on? That's in DMOS waiting tasks. All right, the resource description is 212. The first number is the database ID. 2 is always Tempdb. The next number is the file. It's the first file. The second number is the page number in that file. Now, remember I told you that it was the global allocation map? That's what we're seeing here. Right? We have Tempdb contention, and I hate it. All right, we're going to follow Microsoft's advice. We're going to turn on this trace flag. It helps the round robin later. And I'm going to add 8 data files. You could do this on the fly. It's easy to add them. It's difficult to remove them. All right. So instead of 3 and a bit, we're now up to 5 and a bit. That's wonderful, right? But you mentioned that we're writing to the transaction log when we don't really need to. Check it out. This is log bytes flushed. In terms of bytes, that's K megs, no, technically right. 7 megs per second. Yeah, there's a decimal there. 7 megs per second to the transaction log. And we actually don't need this. In fact, there is a background process whose only job it is to truncate that file every few seconds or every time it gets full. Right? We don't need that data. So maybe there's an opportunity to not use that. Well, in 2014, SQL Server introduced something called memory optimized table value parameters. Remember that type I showed you, that inset? I can't create it because it already exists. Oh, I did create it. Oh, I'm on master. Change to mini LMS. Can't create it because it already exists. All I do is create the table type with this memory optimized on. Why wouldn't you want to do that all the time? If you maybe use these table value parameters to store a ton of data and you know it's going to go to disk, then you're putting larger pressure on the memory than maybe you need to. In our use case, where we actually have very, very tiny table value parameters, I'm going to want to use the memory optimized version. So let's create that type. Now I'm going to adjust the procedure that uses it to use the new kind of type. There's our favorite procedure. All right. There's our parameter. It's inset right now. I'm going to change that to OLTP, online transactional processing, which is a way to describe fast, frequent, short and sweet workloads. All right. Again, let's look at right around 5.5, somewhere in between 5 and 6,000 transactions per second. Once I execute this, all right. We still have a lot of Tempdb activity. Oh, it cleans stuff up. That's the deallocation stuff happening. And now it's at 0. Now it gets me to roughly 10,000 transactions per second. You can look at the CPU, and it's at 100%. So where do I go from here? Well, this workload is CPU bound. It means if this were real life, I'd get my application off a laptop. I'd get my application on another machine, separate from the database. What else would I do? All sorts of things. Put it on a real server. Put
GPU.
GPU? The database can't use that yet.
Well, I didn't.
All right.
So yes.
Yeah.
Well,
Okay.
you're doing the same operation on different data, so
Yeah.
you might have to code it differently, but it might be the spot for it.
So I introduced memory optimized TVPs there. I think they're wonderful. Most people don't use TVPs. So this is kind of a topic near and dear to my heart, but maybe not other people's. No application changes needed. Well, maybe a little one. I left the application running. What I changed was the stored procedure. It avoids Tempdb entirely, which it should have done from the beginning. Not persistent, but that's okay in my situation. Like I said, we don't actually persist procedure argument values. This is exactly what we're using them for. Now, TVPs don't have statistics like temp tables, so in your case, your temp tables might perform better. But my workload is so simple that I want the lightweight TVPs that this gets me. In-memory OLTP elsewhere. Now, memory optimized TVPs are just one small feature of a larger set of features that Microsoft calls in-memory OLTP. In-memory OLTP can get you even faster stuff by maybe avoiding some of the transaction log writes in your user databases. We don't do that at work. We don't have plans to do that at work. We're kind of getting to the limit of what we can support on the database level. Our strategy has shifted away from doing what we can in SQL Server, getting the data out of the database and processing it closer to the application using web services, all sorts of strategies. You can go a long way by not putting data into the database that doesn't need to be there. You'd be surprised. But there are a couple of people. Microsoft worked hard on this feature, and we are so busy, and we recognize that database CPU is more expensive than application CPU from a licensing point of view. SQL Server is not cheap. This in-memory OLTP feature is an enterprise-only feature, and so that bumps the cost up. Right, that's why it's kind of a balancing, and then you have to look at the bottom line. We're not looking at CPU anymore, we're looking at dollar bills, and that's a question for another time. But those are some of the concurrency problems that we tackled in 2015. You take all those concurrency problems, solutions, and you add them to the query turning cost and the query frequency solutions, the application solutions, and all the technical debt stuff that we worked on in 2015. Put them all together, and then you watch 2016 happen, and it was wonderful. It was great. No one was screaming. It was the smoothest semester start, even though it was still busy. I was not busy. On September 1st, I took a day off. I took the family to the beach. It was great. It's really nice to have a solution, have it deploy, and watch your screaming databases go. It's really nice. That's what I love about what I do.